Boy, I gotta say, if you guys have had COVID, hopefully it didn't treat you the way it treated me. But I'm a little older than you guys, but it hasn't been fun. Anyway, we'll get through this. So as we didn't quite get as far on Wednesday as I'd hoped, so I want to go through this problem. I think it's worth the time it takes because it encompasses everything that you might see on a final. The only thing that's not in this problem is a spring, but we have written the final. I think it looks easier to me than the one last quarter, which is good news for you guys. And I think it's doable, although, it's not going to be easy. It's just, it's not as, I think the last quarter's final was really, really hard, but we'll get more to that next week. So I'd like to do this problem today and then talk about momentum. We'll finish momentum on Wednesday. I'll give you back your exams. And then Friday, we'll talk about the final, and voila, there will be. Hard to believe time's gone so quickly. Not what I expected these last 2 weeks. So, but thanks for hanging in there. Okay, so let's look at this one problem here. This is the double pulley that we talked about last time. So now recall that you have a force P that's pushing down on the 5 kilograms, which is causing the 15 kilograms to slide up the hill. As it slides up the hill, it's going to move a certain distance. And so what we want to know is how far does it move, not only when the 5 kilograms drops 1 meter, but how far does it continue to move afterwards, given that it'll have some initial velocity. And so hopefully you had deep thoughts about that in the last couple of days since we had class on Wednesday, but just in case, we'll go through it. All right. So there's our drawing. So there we have. So again, here we're going to label this distance SA. That'll be distance SB. Now, first thing when we look at this is we can see that the velocity of A is going to equal RA times omega C. And so that relationship also falls for VB is going to equal RB times omega C. So what that tells me is that I can write VB equals the radius of B over the radius of A times VA, or I can determine what the relationship is. So it turns out that if I take VB and I put 0.15 over 0.25 and then multiply by VA, this number here is 0.6. So VB equals 0.6 of VA. All right. So whatever the speed of B is, it's 0.6 of VA. So we'll have that relationship to start with. And then we also know that the distance SA is going to equal to RA theta C. But that's not as important because we know that this distance SA has been already defined by 1 meter. Now, we're going to use our energy to do this problem. So we know it's going to be T1 plus U1 to 2 equals T2. And so we'll start off with what is going to be T1. So now we know that T1 actually is going to be 0 because we start at rest. So we can put a 0 through that. So let's figure out what T2 is. Now T2 is just going to be the kinetic energy of the system. So T2 equals, and if we write this out, it's going to be 1/2 MA times VA squared plus 1/2 MB VB squared plus 1/2 IC over omega C squared. Okay, and that's all the kinetic energy we have: the rotation of the disc or the pulley and the two sliding objects. So we can we know that this relationship of omega C, we know that omega C, if we want to get it in terms of VA, we know that omega C equals VA over RA, right? So what I can do then is I'm going to do some substitution. One thing I also know is that VB and VA can be substituted also, right? So what I want to do is I want to get T2 in terms of VA, just one variable. And because I'm looking for VA, right? I want to know what is the velocity of A as it hits the ground. So I really want to eliminate this and get that, and still having issues with focus, sorry. And so if I rearrange this, I can write this as 1/2 VA squared, and that's going to be multiplied by MA plus MB times RB over RA squared plus IC over RA squared. And so how did I get that? Well, I used this relationship here. I know that VA squared, and this is omega C. So I substituted that in for this, right? And so this would have been VA squared over RA squared in here. And then I just factored that out. And then to get this relationship, I just used this up here and I squared it. So basically I said VB squared equals this squared. So all that's left is this ratio, which is this. Okay, so hopefully you see what I did there. But I just factored that out. So now I can just put in my numbers and I get 1/2, and then it's just going to be 5 kilograms plus 15 kilograms. And then that ratio ends up being 0.36 when you plug in RB squared over RA squared. And then that's going to be plus, oh, and IC I calculated up here, backing up. Remember that we were given the radius of gyration. So if that's the case, remember that you want to multiply the radius of gyration by the mass. And so the radius of gyration squared times the mass is going to give you I. So we get I to be 0.384. So we plug that in here, 0.384, and divide that by RA squared, which was 0.0625. Okay, and then all of that factor out VA squared. So that was kind of a long-winded, but that's what we needed. And so we end up with T2 equals 8.272 VA squared. All right, and that's what we want. All right, so we'll have that. So that's the first part. So we have that of this, right? So now we need to figure out what this is. Okay, so once we get this, then we should be to the point where the only unknown is our VA squared. So let's figure out what U1 to 2 is. Now, before we do that, let's go back up here and look at what we have. So there should be 4 things happening with U1 to 2. We have the 200 newtons times distance. So you have a force times a distance. You have a change in gravitational potential energy from here to here. That's the second. You have a change in gravitational potential energy from here to here. That's the third. And you have the friction over distance. So that's the fourth. So if we write those out, we get U1 to 2 is equal to the force, and I'm going to call that distance SA, plus the mass A times G times SA, minus the friction force times the distance SB, and then minus mg times distance SB times sine 30. All right. So hopefully everyone sees that this is just mgh, right? This here is your height in the mgh equation. Because if we have our triangle like this, and we go from here to here, then that distance is going to be just this opposite side here. So that's where our h comes from. So if we plug in our numbers, we get P times SA. So we have, so let's just write U1 to 2. So P is 200 newtons, right? So that's this, times SA, 1 meter. And then plus our MA, which is what, 5 kilograms times 9.8, 1, times SA, which again is 1 meter. So that's this. We don't have our friction though. So how are we going to do that? So coming back up to this sheet, let's figure out what our friction is. And so if we have our incline like this, we know that if we look at our block, then we know that that is going to be our normal force. We know that that's going to be mg. We know that's tension. And we know our friction force is going to go that way. Sorry, it's kind of sloppy. And so we have friction force going that way, tension, mg, so forth. So we know that there's no acceleration in the y direction. So if we sum the forces to the y to 0, then you should be able to see that the normal force is just equal to mg cosine 30 degrees. And so that gives me a value of 127.3 newtons. And since mu kinetic is 0.2, that means that my friction force is just 0.2 times that, or 25.46. So this should be all review here, how we got that. So we have our friction force is 25.46 newtons. So we can put that then in here, minus 25.46 newtons. Now, SB, remember that we determined that SA is 1 meter, SB is going to be 0.6. So that means that we're only going to move for every 1 meter we move here, we're going to move 0.6 meters here based on the ratio of these. So that means that I only am going to have a 0.6 meters that this force will move. And then lastly, minus, that's going to be minus this, which is going to be the 15 kilograms times 9.81 times 0.5. Sorry, it's getting messy. And then that's, of course, times 0.6. All right, so that's SA, that's sine of 30, and then that. All right, so we get a total, if we add all the energy up, U1 to 2, we get a total of 190.2 joules. Any questions so far? My huge class of 10 people. I appreciate you coming. It would have been kind of depressing to only lecture to like 2 people. So I realize it is a holiday weekend and online classes are not that fun, but I do appreciate you coming and listening to me. All right, so no questions, good so far. So now that we have that, we can figure out the velocity of A, right? Because we know, again, recall that we knew that T1 plus U1 to 2 equaled T2. So we have now 100 and 0. So we have 190.2 for our U1 to 2, and that just equals our 8.272 VA squared. And solving for VA, we get a value of 4.80 meters per second. All right, so that's the first part. And then the second part is to figure out how far does block B slide after before total. And so we know that block B is going to be traveling at a certain velocity when it goes, it's 0.6 meters, and then it's going to continue a certain distance on. Now we can look at this and we know because of the ratios, we know that for one is velocity of B is going to be equal to the ratio of RB over RA times velocity of A, right? Like we showed at the beginning. So if we say VB equals 0.6 of 4.8, we get a VB to be 2.88 meters per second. Also, we know that our omega C, our rotational, is going to be VB over RB. And that's going to be equal to 2.88 meters per second divided by 0.15 meters. And so we end up with omega C equal to 19.20 radians per second. Okay, so we'll need those values. Now, next step is, this on the back of this. Okay, so we'll save paper. So the next step is to figure out how much, how far did B go beyond the 0.6 meters. So for that, we're going to say T3 plus U3 to 4 equals T4. So this is going to be the kinetic energy where the block is moving at 2.88 meters per second. Block A is moving at 0. And then this will be how much gravitational and friction we have to overcome. And then this, of course, at the final is going to be 0 because it's going to stop. So if we write this out, we know that T3 will just equal 1/2 MB VB squared plus 1/2 IC omega C squared. And that's it, because A is no longer in the picture because A has stopped moving. It's already hit the ground. So if we plug in our numbers, we get 1/2 15 times 2.88 squared plus 1/2. And then we have our 0.384. And then that's going to be times our omega 19.2 squared. So we have all our numbers so we can get our value. And that's just going to be 133. So 133.0 joules. All right. And then we need our U3 to 4. And so that's going to equal to the negative friction force times SB prime. So SB prime is the distance it's gone once the block A is stopped. And then that's going to be minus mg sine 30 times SB prime. All right. So if we go ahead and factor out SB, we get this equals SB prime. And then that's going to be what? It's going to be friction force, which is negative 25.46. And then that's going to be minus 15 kilograms, 9.8 times 0.5. So we end up with a total value of negative 98.96 SB, sorry, prime. All right. So that's pretty much all we need then at that point. So we have T3, we have that. So we know it's going to be 133.0 minus 98.96 times SB prime, all equals 0. So SB prime equals 1.34 meters. So the total distance is going to be that plus the 0.6 that it moved, right? It moved 0.6 meters at when A was moving. And so the total, the answer, SB total, is going to equal 1.94 meters. All right. Makes sense? Hopefully.
Professor Neighbor,
Yes.
why do you multiply by SB with the dash over it or whatever?
Oh, so the SB prime is
SB prime.
that's the distance. So if we look back to this thing moved when this went from one down here, then this moved 0.6, right? So this moved 1 meter, that moved 0.6 meters. And then it had a velocity of 2.88 meters per second. So that meant it kept moving past that. And so that's my SB prime, is that distance past it.
Okay.
So in order to figure that out, I have to figure out, I know it has kinetic energy at this point, right? So it's 2.88, just like I knew this had a speed, right? Because it was being pulled by this thing. And so I just multiply force times distance, so SB prime times the friction distance. And then I also have to count for the fact that it's going up the hill. So I have to count. So essentially the 2.88 meters per second gives that 1/2 mv squared. That's bled off by the force times distance of friction and the change in height due to gravity.
Okay.
Make sense?
Yes, that does make sense.
Okay, good. So you can see there's a new this problem was little long. I wouldn't say it's tedious, but I mean it follows a systematic order, and I think that's the important takeaway, is that if you can understand the different steps in this, then you should be okay. I don't think that there's going to be anything in terms of energy more complicated than this on the final. So I don't think we'd add a spring in there too. And actually, as I said, I think at the beginning, I've seen the final. I think the final's actually, it's easier than the final was last quarter. So, but I mean, obviously that doesn't help you guys, and you want to be able to do what we have and be successful. So, but we'll talk about that more next week. All right.
Professor, can you please go to the second page of work that you have? I just missed something. Like the last calculation, the U3 to 4.
Oh, let's see where this one. Is that the one you're looking for?
Yes, it is. Thank you. Yeah, I'm good. I just screenshotted it.
Okay, thank you. I'm also recording this too, and I'll post it on Canvas for your viewing pleasure. So if you're, you can always make some popcorn, invite your sweetie over, and watch this over and over again. I don't have the time to add good music to it though, unfortunately. All right, so let's go back to this slide. So this is chapter 17.2, momentum. And these first few slides are just kind of an overview of what you should already be familiar with. For example, we know that if you have a system of momentum, when it comes to linear momentum, we know that if you take your mv plus your force integral over dt, then you end up with a final momentum. But I think what I want to show you, it's probably easier just to write it out. So I'm not sure you understand this. So let me go ahead and do this. So if you have, recall that with linear momentum, like the slide showed, we know that mv, that's our initial. And then we had plus the integral of f dt. So that was our impulse. Then that equaled our final. And we did problems like that, and it made sense. And so for the analog to that with rotational or angular momentum is we know that that's going to be I omega. So I being the equivalent of mass and omega being the equivalent of velocity. And so we have I, sorry, I meant to put the bar over the I. So this is the about the center of, and so again, I is always about the centroid of your object. So you have I omega 1, and then we have plus, now instead of force times time, we have the integral, and it's actually the sum of all the integrals of the moment about g dt. And so what that's saying is that all of the moments about the center of gravity times over time, that's then going to give you your final angular momentum, omega final. Because remember that f times distance is equal to a moment, right? And that's really what angular momentum is. It's the moment of momentum, and that's why we use m. Now, this assumes that you're about the center. So this is your blob, there's g, you're rotating about g. But as we found in the previous chapter with F equals ma, maybe you're about a different point P over here. So if that's the case, then you're going to write it similar. You're going to have I bar omega 1, but then you're going to have to add in this mv1. So that's your linear momentum times your d perpendicular. And that's the line of action from the point of interest to your center of gravity. And so here, moment of momentum, right? Linear momentum times distance. And then you're also going to add to that any moments you have. So moments about p dt. And then that's going to give you your final I omega plus your m v2 d perpendicular. So this encompasses pretty much everything in this case, is that because now you're taking into account the moment of momentum due to a velocity that's not at the center of gravity, and you're taking any rotational moments that are occurring over time. And this is kind of this is what I consider your general form equation. And so don't be intimidated by it. It's really just a reapplication of what we've already been doing. And we're going to do a couple examples to make sure you understand it. But so if we go back and look at this, then this is really what this is kind of summarizes it. It says that if you have your this is kind of what I just talked about, in the sense is that this is your linear momentum, but you can replace it with your linear momentum at the center of gravity plus your I omega. And then you can also do the same thing. And so these 3 slides, I probably should have added another slide in there, but what I would say is go back and look at over section 17.2, because it does discuss the derivation. And I'm not so worried that you understand the derivation. I'm more concerned that you can apply the actual relationship of angular momentum versus linear momentum. So for example, if we look at a simple example like this, you can see that in this case, you have a cube and a cylinder, right? And so in this case, we're looking at this equation here. Okay. Oh, sorry, I'm not. So I'm drawing on the thing, but you can't see it. But so let's just you can see the problem, and then let me draw it out for you. So we're going to use this equation here for that problem, because what do we have? We have a cube. With the cylinder. Now, the cylinder, if we look at the two together, they're going to have a composite moment of inertia. So we know that I bar is going to equal essentially I bar of the cube plus I bar of the cylinder. So that's going to equal 1/12 mass times length side plus L squared. So it's essentially each side. So you could do it with the rectangle, would be A squared plus B squared. But since they're all the same, it's just L squared plus L squared, or you could put L to the fourth. And so then for the cube, we know that's going to be 1/2 mr squared, not for the cube, for the cylinder. So the cube is 1/2 m L plus L, and that's plus 1/2 mr squared. So you'd be given these on a table, but point is that you can plug in the numbers and you can get a value for this, which is going to be 1.475 kilogram meter squared. So you have that. That's not a problem getting that. Then you look at this relationship, though, it breaks down to I omega 1 plus the moment times time equals I omega 2. Now we're told that we're given omega 1, that's 1,000 RPM, and we're given omega 2, and that's going to be 2,000 RPM. And we're given our moment is 20 Newton meters. So it's really, this is just a plug-in number problem, but I wanted to show you not for the numbers, but for the relationship. So you know that you have your moment of inertia times your speed. So that's going to be just I times, and of course we're going to put that in radians, 100 pi over 3. And then that's going to be plus our moment, 20 times our time. And then that's going to equal our final I times 200 pi over 3. And so we can plug in I, and we can solve for t, and we get a t equal to 7.72 seconds. But notice that was all that you needed for the relationship. And so this takeaway is, when you look at a problem on the test, is make sure that you identify, what is it asking? So if as soon as you see time in it, then that's going to be an impulse momentum problem, because we don't deal with time in energy. Energy is distance. So force over distance is energy. And then force and acceleration, that's going to be F equals ma. So there's things that you can do to help yourself understand what type of problem it's coming from, simply by looking at the wording of the problem. All right, so let's look at this problem. It's now in this case we have a carriage. We have our carriage and we have wheels. All right. So here's this P is 3 pounds, and we're given that there's a 0.2 pound force P has been applied, and over a time of 0.5 seconds. So we want to know what is the velocity. So it starts at rest and then it ends at some velocity. So here's my drawing. So we have 3 pounds, we have A, B, we have some force P going here. So if we draw these, we know that we have VC, so that's just the carriage part. That just has a velocity C to it, and that's it. And then if we look at the wheel below it, we know, and this is if we just looked at magnified A, we know that if you looked at A or B, they're both going to be identical, but notice how I call this instant center. We talked about instant center, the point where at that moment in time, there's no motion. And so this has a velocity of 0. So we can relate that to VA and VC. So VA is going to be at the center, VC is going to be at the top because of its location with respect to the carriage and the wheel. So we can see that VC is going to be equal to whatever omega A is times 2R, right? And that's just the definition of instant center. We know that that's this perpendicular line here. And so that's how we know that that equals that. But even if you didn't do the instant center, I think you could see that VA is going to be half of or twice of VC. So VA is half of VC. And so VC is going to move quicker because it's on the outside of the circle. So we have this relationship, VA equals 1/2 VC. Then if we come down to this, we have our impulse momentum diagram. And so what that represents is 0, because that's initial. There's no impulse or momentum at the beginning. And then this is our impulse here. So we have M1, V1, 0 plus our impulse. So our impulse is going to be our force times time. We have our force times time of friction. We have normal force T. We have F2 time, and we have N2 time. And then the last is going to be the N, which is just going to be MC times VC, whatever that is. So the final velocity. So this is MCVC. Sorry, it's a little small. Okay. So if we write an equation, remember that for our impulse momentum, we have essentially 0 plus, and then we write out all of this. It's going to be P delta T minus, and we're going to make this direction here positive because that's the direction we're going in for simplicity. So P delta T minus F1 delta T minus F2 delta T equals MCVC. Okay. Does that make sense how I got that? So I'm just looking at this block. Now, I also want to, so that's my first equation. We're going to come back to that. What I also want to do is I want to look at the wheel itself. So I draw one wheel, that's going to be 0, and then draw the second wheel. And so for that one, it's going to look like this. It's going to have a normal force A times T. It's going to have friction force A times T or delta T. Up here, I'm going to call this my F1, just like this was F1. This is going to be F1, and that's going to be my N1. So F1T and N1T, all right? And then that is going to equal, for my final disk, it's going to equal the center, MA, VA, and then it's going to be, and I'm about the center, so I'm going to call that IG omega A. All right. So I'm just going about the center, not any other random points. So my next thing I'm going to do is I'm going to take the moment about the instant center. Now, because of that, I have to count for, because I have my, I have to count for the distances and the moments. So and I'll explain that as I write this down. So moment about the instant center based on this. Now, where's my instant center? It's down here, isn't it? That's my instant center on the wheel. It's at the bottom. So that means that NA and FA are going to be 0. They're not going to have any contribution because they're at the point. N1 isn't. So the only one really is F1T, isn't it? So I'll write that as F1 delta T, or T, doesn't matter if you put the delta, but let's simplistically, let's make it delta just so we're consistent everywhere. All right. So delta T, and then that's how far is it from the instant center? It's 2 radii. All right. Then that is going to be equal, because that's my moment. That's the only part of the only thing creating a moment. Then I know that has to equal what? My IG times the omega A. But I also have to include this piece here, right? Because this is also creating a moment about that point due to its motion. So that's going to be plus MA VA times R, right? So that's your moment of momentum with respect to this. That's a moment of momentum, okay? That's the important part. That's the part that'll trip you up, is getting that, okay? So make sure that when you do these types of problems, you go back to your fundamental equation, which was the M1 V1 plus the M T and sum of all the MTs, and then plus any MVD perpendiculars, right? You want to include those like we talked about. So you have your IG, your WA, and then your MAVA times R. Okay, so far so good. So what we're going to do is we're going to do some substitution now. We know that this is still going to be F1 delta T 2R. Now IG, I know that for a disk, it's 1/2 mr squared. So I'm going to put 1/2 mr squared. And then I know that for WA, that just equals VC over 2R, doesn't it? So I just replaced WA with VC over 2R, and I replaced I at the center of a cylinder with 1/2 mr squared. And then I also know that that's going to be plus, and then this is just going to be MA, right? And then, but I know that VA is what? 1/2 VC, right? I put that, and then that's times R also, okay? So I know that VA is 1/2 VC. I found that up here, remember? VA equals 1/2 VC. And so I just went ahead and I just put these substitution. All right. So now I can simplify this. This becomes F1 delta T equals 3/8 MA VC. And so what you can see is that the R is going to disappear. So R, because this is R squared over R, so the R's are all going to disappear. This is 1/2, this is 1/4. So that plus that is 3/4. Then I divide both sides by 2 and I get 3/8. So that's how I got that. So this is my simplified version. So this is for, of course, I've done this for disk A. But I know that the same exists for disk B, right? If I were to write F2 delta T, that would equal 3/8 MB VC for disk B. But I know that MB equals MA, so I can write this as MA also. So with that, what I can do is I can go back to my equation, which was, oh, this one. So what we're going to do is we're going to go back to this equation, 0 plus P delta t minus F1 delta t minus F2 delta t equals mcvc. So we're going to go back to that equation and notice that now we have F1 delta t, F2 delta t. We can substitute those into the here respectively. So if we do that, we end up with P times delta t minus 3/8 MA VC minus 3/8 MB VC equals MCVC. And so, but because MB and MA are the same, then I can simplify this further to be P times T. I'm going to say delta T and T are the same. So delta T equals T. And what I'll have is this is going to be equal to 0.75 MA plus the mass of C all times VC. So that was just my simplification. So now I'm pretty much done, right? Because what I want is VC. So VC equals P times T over 0.75 MA plus MC, which is equal to what? 0.2 pounds over 0.5 seconds all over 0.75. And remember that this is 2 pounds, but it's mass, so it's 32.2. You got to divide it to get to slugs, plus 3.0 over 32.2. All right. And so what we end up with is 0.716 feet per second. Okay. Make sense? Something to chew on, I realize. So on this should get you though to the point where you can do all the homework problems. And I'm not saying the homework problems are trivial. Some of them are a bit challenging, so do the best you can. I'll be in office, of course, next Tuesday. If you want to drop in and ask questions, I'll have office hours Wednesday too. So next Wednesday, what we'll do is we'll go over, we'll continue talking about and finish up momentum, and then we'll talk about your guys' tests. Okay. Well, I hope you guys have a good weekend. Try to have some fun, not just think about school. And otherwise, I will see you soon. Thanks, everyone.
Professor Newber.
Yes.
So if we missed like homework and we want to use our late pass, how do we go about doing that? Because I couldn't find like a submittal thing on Canvas.
You just submit it as you normally would. It'll tell me if it's late, and then I go and I check my list. So just submit it. Okay.
All right. Sounds good.
All right.
Thank you.
Thank you.
And Professor, will class on Wednesday be in person?
Yes.